Hey y'all, welcome back. Today we are going to go over the 2025 AP Calculus AB free response questions. These were released about a week ago, just a couple of days after the actual exam. The scoring guidelines have not been released, but once they are released, if there's anything that I've missed, any points that I haven't accounted for, I'll make sure to write about it in the description of this video. Now, on these free response questions, there are 2 calculator required questions, and I'm going to be using Desmos as my calculator of choice. And then there's 4 non-calculator questions. This is pretty consistent from year to year, so hopefully in the future you will still have 2 calculator and 4 non-calculator. So let's go ahead and begin. Number 1 says an invasive species of plant appears in a fruit grove at time 0 and begins to spread. The function c, defined by 7.6 times the arctangent of 0.2t, models the number of acres in the fruit grove affected by the species t weeks after the species appears. It can be shown that c prime, or the derivative of c, is 38 over 25 plus t squared. Kind of nice that you don't have to actually find that derivative. They just give it right to you. It also says that your calculator should be in radian mode, and whether you're using a TI-84 or Desmos, it defaults to radians, so hopefully that's not an issue for you. Now, part A says find the average number of acres affected by the invasive species from time equals 0 to time equals 4 weeks. Show the setup for your calculations. Now, on these calculator problems, there's usually not a ton of work that you have to show. Usually, all you need to show is just your setup and your answer. Now, sometimes they want a justification for your answer, so you do have to say something to that effect. But on this particular problem, we just need to write our setup. We're going to type it into Desmos and then get our answer. So to find the average value of a function, maybe I'll just write that out. And I'm going to write this out just kind of, sort of generically. So average value of a function, we'll call it f of x from a to b, can be computed by finding the integral from a to b of f of x dx divided by the length of the interval, which would be b minus a. So that is how you calculate the average value in general. And for this case, we're going to have the integral from 0 to 4 of ct, instead of f of x, dt over 4 minus 0. Now, this is something we'll just go ahead and type into Desmos. We will get an answer just right away. But as far as the setup for your calculations, that's what this is. So let's move on over to Desmos here. Pull this up. Okay, and because there are going to be multiple parts to this question, I'm going to type out what C of t is, just because I'm going to be kind of referring back to it quite a bit. So arctangent 0.2t. That's it. Yeah, okay, so there's my function. I don't really care what it looks like, but I just want to refer back to it. So to calculate the average number of acres, we're going to do the integral from 0 to 4 of c of t dt, all divided by 4 minus 0. And so we get approximately 2.778. Make sure you go out 3 decimal places. It doesn't matter if you round or truncate. In this case, you get the same thing because it would round down anyway. But I usually advise just to go ahead and truncate. Don't even look at the 4th decimal place because you don't need it. Okay, so that's it. So we've got our setup, and we've got our answer. And I believe that's all we're going to need to get all the points for that problem. Part B says find the time t when the instantaneous rate of change of c equals the average rate of change of c over the time interval 0 to 4. Show the setup for your calculations. So let's break this down. We want the value t when the instantaneous rate of change equals the average rate of change. So let's write that out. The instantaneous, can I spell instantaneous? Oh, I have it written right up there. The instantaneous rate of change, we want that to be equal to the average rate of change on the interval 0 to 4. So the the instantaneous rate of change, that's just the derivative of c at some time. So I'm just going to say c prime t. We want that to be equal to the average rate of change on the interval 0 to 4. Now, the way to calculate average rate of change is you just simply use the endpoints of your interval and plug those into your basic slope formula. You're trying to find the slope of the secant line between those 2 points. So this is going to be c of 4 minus c of 0 over 4 minus 0. So we're looking for what t value does this equation hold. So going back to Desmos, I'm going to type in c prime t, and I want to kind of see what that graph looks like. So I'm going to say y equals c prime t and hide the original c. Okay, so there's my c prime t. I really only care about the interval 0 to 4, so I'm going to make that domain restriction on here so I'm not getting distracted by any other information. All right, let's go ahead and zoom in here. And then I want to know, when is that equal to the average rate of change? C of 4 minus C of 0 over, and this is just going to be a constant, 4 minus 0. So in other words, I want to know, when does this curve actually equal this? And I think the easiest way to find that is just to go ahead and write both of these as 2 separate equations and just find where they intersect. And we can see that they intersect right here at t equals 2.154. And that would be in weeks. Okay, so again, we've got our setup and we've got our answer. Hopefully there's nothing more that we need to show there. I really can't really imagine what else you would need. All right, part C. It says, assume that the invasive species continues to spread according to the given model for all times t greater than 0. Write a limit expression that describes the end behavior of the rate of change in the number of acres affected by the species. Okay, so the rate of change in the number of acres, that is the rate of change of c. So that's c prime. So basically what we're trying to say here is that we have this function c prime, and we want to know what the end behavior is for positive values of t. In other words, we want to find the limit as t goes to infinity. Now, what does that equal? That's what it's really asking. It says evaluate this limit expression. So we probably got 1 point just by setting up that limit, but we want to know, what does it equal? So we're not really going to use Desmos for this, although you could absolutely just type it in and kind of see where it equals. We're going to go up back to where they actually gave us the equation for c prime up here. Okay, there's c prime. It's 38 over 25 plus t squared. So this is going to be the limit as t approaches infinity of, oh gosh, I forgot it already, 38 over 25 plus t squared. I want to know, what does that equal? So this is going to take us back all the way to Unit 1 when we originally learned how to evaluate limits as x approaches infinity, or in this case, t approaches infinity. And we want to look at both the degrees of the numerator and the denominator here, because we do have just a classic rational function and nothing really weird happening with it. And anytime you have a rational function that has a denominator where the degree is bigger than the numerator, that denominator is going to be growing much faster. And in this case, the numerator is just constant anyway, so it's not even growing. So when the denominator grows faster than the numerator, we say the limit as t approaches infinity is 0. And that's it. Part D. It says at time equals 4 weeks after the invasive species appears in the fruit grove, measures are taken to counter the spread of the species. All right, let's get rid of that species. The function a, defined by a of t equals c of t minus this integral, models the number of acres affected by the species over the time interval 4 to 36. At what time in that interval does a attain its maximum value? Justify your answer. So this is going to require an application of the extreme value theorem, where we need to find the absolute maximum value of that function. And the basic strategy for finding the maximum value is to identify first where are the critical values, and then what are the values of the endpoints, and test each ones to see which one's the biggest one. Okay, so we're basically going to make a table with the endpoints 4 and 36, and then any see t and a of t, and any critical values that we might find. In other words, when is the derivative equal to 0? So let's type in that equation for a. I'm going to hide all these in Desmos. And you can just type this in directly. You don't have to do anything fancy with it. So you have c of t minus the integral from 4 to t, 0.1 times the natural log of x dx. Okay. So here we go. We can also restrict this domain to be t values that we want. Let me drag this out so we can actually see everything. We're going to go from 4 to 36. Okay, and I'm going to zoom out on this graph just to kind of get a feel for what's happening here. It looks like we're going to only have one critical value or one relative extreme here. That's probably going to be our answer, 11.441. But let's verify using the extreme value theorem. So first things first, let's evaluate a of 4. Okay, so it's 5.128. And let's evaluate a of 36. Okay, 1.743. Now let's find any critical values. In other words, we want to know when is the derivative of a equal to 0. Okay, so I'm looking at a prime here. Looks like it's equal to 0 at this point right here. Okay, so we've got at time 11.4417. You could also just call it 442 probably. And then that does correspond with what I thought was going to be the local maximum. So we're having a pretty good indication that that's going to be our answer. And our output there is 7.316 or 7 if you round it. But that's really not going to make a difference because that is the maximum value. So this is a critical point where a prime is 0. It's really the only one on that interval. So there we go. So that is the maximum value. But the question, let's make sure we're answering the question that's being asked. It says, at what time does it attain the maximum value? So we can say that A attains its max value at t equals 11.441. I'm just going to truncate there. The justification is just going to be that table. Okay, and that does it for problem 1. Let's go to problem 2. Number 2 says the shaded region R is bounded by the graphs of the functions f and g, where f is x squared minus 2x. It looks like, they have it labeled, so that's nice. And g of x is x plus sine of pi x, as shown in the figure. Again, your calculator should be in radian mode, so hopefully you have not changed it to degree mode. If you have, make sure you go back and change that back. But your calculator should default to radians, so again, this should not be an issue. Part A says find the area of region R. Show the setup for your calculations. And just like with problem 1, you don't have to show a whole lot of work. You really just want to communicate what are you typing into the computer and what is your answer. So what's your setup and what is your solution? And that's really all you should be writing out. So in this case, we want to find the value of the area of region R. And so we are going to integrate the difference between f and g from 0 to 3. Notice how the beginning of the interval starts at 0, the end of the interval starts at 3. So we're going to integrate from 0 to 3. Now, how do we find this area? Now, what's kind of interesting here is that the g function is on top. So we actually want to do g minus f. So g of x minus f of x. And make sure you have your little dx on there. If you're using Desmos, it'll give you a little error if you forget that. So hopefully that can be a little reminder to include that. But then we're just going to say, what does this equal? So I'm going to bounce on over to Desmos again and type in the two functions that we're using here. F of x equals x squared minus 2x, and g of x equals x plus sine of pi x. Now for both of these equations, it looks like we're really only interested between 0 and 3. So I'm going to restrict both of these just because that way I can really kind of focus in on this region that you see in here. I don't really care what else is happening in the graph. If something comes up where we need to look outside of that little interval, then we'll go back and adjust this. But for now, I'm just going to say that my x values, I only want them to be in between 0 and 3. And so that way we can see exactly what we're seeing on the diagram here. And as I zoom in, you can see that that region looks pretty similar. So I'm pretty sure we typed that in right. Okay, so now let's go ahead and calculate that integral. So the integral from 0 to 3 of g of x minus f of x dx, and we get our answer for that one, which is 5.13. I'm going to leave it as 6. If you round it up to 7, that's okay too. But as I've said many, many times, I like truncating on this exam because it gives you one less decision to make and one less potential error to make as well. So yeah, there's the area of R. We're not given any units here, so we don't want to invent any units. You don't want to say like square inches, square meters, anything like that. Just give the numerical value. Part B says region R is the base of a solid. For the solid at each x, the cross-section perpendicular to the x-axis is a rectangle. Okay, area of a rectangle is base times height. Just keep that in mind. The height is x, and the base is in region R. Find the volume of the solid. Show the setup for the calculations. So basically here, we're going to, for all of these volume questions, we're going to stick to the integral from a to b of the area of the cross-section times dx. Now, in this case, the cross-section is a rectangle, and this is going to be a little hard to sketch out here, but I'm going to just try. And that is that, like, if we take any particular cross-section, so let's say, like, here at, like, 1.5-ish. This right here is the base, and then the height is x. So the height would be, like, 1.5. So if I'm trying to draw this in the third dimension here, you know, you've got this side right here, the base, which is g minus f, and the height is x. And so for each one of these, you know, as x increases, the height's going to increase. So like here, we got g minus f, and here's x. And so you're going to have, like, here's a little tiny, this one's going to be a little tiny rectangle because the x isn't quite as big. But you can see as x increases, so does the height of the rectangle. So by the time we get to 3, you know, right here, we have the tallest rectangle out there, which should be approaching 3. So anyway, each one of these little shapes, each one of these little cross sections is a rectangle, and the way we calculate area of a rectangle is base times height. So we're going to have the integral from 0 to 3 of the base area, which is going to be base times height, where the base is g minus f, or I'll write it as g of x minus f of x, and the height is just x. So we just want to multiply that by x, and of course we have our dx. So that's what we're going to type into Desmos. It's very similar to the one we just did, so I'm just going to copy paste here and just multiply that factor by an x. Okay, there we go. I get 7.704. You could write 7.705, and you get full credit there. Rounding's fine, but again, I'm going to stick to truncating. Part C, it says write but do not evaluate, which is kind of interesting because we're using the calculator, so evaluating really wouldn't be a big deal here. But it says an integral expression for the volume of the solid generated when the region R is rotated about the horizontal line y equals -2. So if we look back up here, and I'm going to erase my little rectangles here because it's getting kind of cluttered. In fact, I'm going to erase all my little markings on here and draw the line y equals -2, just so you can get a visual, or hopefully assist you in getting the visual. So I'm not much of an artist, but here's y equals -2. What we're doing is we're taking this entire region here and revolving it around that line. So in other words, like let's say at x equals 1, okay, we've got like this little section here is getting revolved like a washer, like around this line. So it's going to look like something like this, right? And you're going to have that cross section at every location between 0 and 3. So like, get a little further out and this circle is going to be much bigger. See, it's really kind of hard to sketch here. But basically, each cross section is going to be what we call a washer, which is a circle with a little circular hole missing through it. So hopefully that little visual it doesn't confuse you more. But the way we're going to approach this is actually the same way as we approached the last one, which we're going to use this integral from a to b of the cross-sectional area times dx. The challenge here is coming up with that cross-sectional area, which is the area of the big circle minus the area of the small circle. So I'm gonna write it just like that. The area of a circle is pi r squared. So we have to be careful about how we. So maybe I'll write this, and I'm going to erase the r. But I'm just going to set it up initially. The pi big R squared is going to be this, like the bigger circle. Let me draw one more of these. I'm going to draw another one of these so you can kind of see where the big and the small circles are coming from. Minus pi times little radius squared. Of course, we need a dx on there, but this is just kind of getting us set up. I wouldn't even write that, honestly, because there is no reference to r, and a big R is already, the area of the region. But I'm really just trying to communicate here is the big radius and the small radius. So if I'm looking at this circle with the circle missing, the small radius is this right here. The big radius is this distance right here. So the big radius is going to be the distance between function g and -2. In other words, it's going to be g minus -2. So that big radius, and let me just erase the rest of this, is going to be g minus -2, which is really g plus 2. So that's pi r squared minus the little hole, this little circular hole here that's missing, which is going to be f plus 2. It's the distance between the function f and -2. So f minus -2 is f plus 2. Oh, I left off the little pi there. So we got pi r squared minus pi r squared dx. I think I've got all my parentheses counted for. Just like take another look at that. Yeah, and so I'm going to clean this up just a little bit. I'm going to change this g to gx and change that f to f of x, so I don't have any issues typing it into Desmos. And so this is good. This is actually a pretty good answer here. You can just leave it like this. And actually, yeah, I don't even have to type it into Desmos because we don't have to evaluate it. But oftentimes when you see an equation, an expression written like this, a lot of times you'll see this pi factored out, which you don't have to do. But let's say like if this was a multiple choice question, you're almost always going to see that pi factored out. And it'll look a little bit more like this. So you do not have to rewrite it like this. It is a little cleaner, not by much, but if that's how you wrote it, that's totally fine too. I kind of like not factoring it out. Most of the time I do like factoring. But in this case, I just think because of the context of how you're calculating that area, that's important, right? Is to really show that you're understanding where these numbers are coming from. Just having that pi r squared in there really gets to the concept of the fact that you're finding the area of a circle, right? Pi r squared. So it's a big circle minus the little circle. So either one of these is fine. Yeah, I think you'll be good with either one of those. There's a lot of parentheses there, so make sure you double check and kind of reread what you've written just to make sure you're not like missing a closed parenthesis anywhere, because that can get you minus a point. I'm really like this expression here, just like there's so many parentheses there. I really think I got them all, but I'm like rereading this 4 or 5 times. I think we're good. Okay, part D. It says it can be shown that the derivative of g is 1 plus pi cosine pi x. Find the value of x between 0 and 1, at which the line is tangent to the graph of f is parallel to the line tangent to the graph of g. So in order for it to be parallel, what we need are the slopes of the tangent lines to be equal. So the slope of the tangent line of f is just f prime x, and the slope of the line tangent to G is just G prime X. So we need F prime to equal G prime on this interval. I don't really know why they gave you G prime here, honestly. Like, this is really, I think all you need is just to show that these are the same. So if I go to Desmos here, we're going to come right back, and I guess we could leave all that in there. I'm going to hide the original functions F and G, because really all I want is F prime, and I want G prime. They really didn't even have to give you G prime here. I'm not sure. There could be something that they're looking for here. I'm not sure. But here, notice that there's a couple different intersection points here, and that's because right now we're just, our domain restriction was from 0 to 3, but what we really want is the domain restriction between 0 and 1 for this problem. So x 0 is less than x is less than 1. Do the same thing for the other one, for G prime. Oops. There we go. And here we see we just have one point of intersection here, and it's at x is 0.675. Yeah, I'm kind of wondering, like, if there's anything we're missing here. I'm not really sure that there is. I suppose you could differentiate f, which would be 2x minus 2. And so you're looking to solve the equation. When is 2x minus 2 equal to 1 plus pi cosine of pi x? At the end of the day, you're going to need a calculator anyway to solve for x. So I don't know that you're really getting any advantage out of writing it like that. I think writing f prime equals g prime is sufficient, although we'll definitely get some clarification on that once the actual scoring guidelines come out. But that should be it. It's 0.675. If you got that and you wrote down something about how, where that problem came from, I'm going to assume you're going to get full credit on that. Okay, so that's the end of the calculator section. There's only 2 problems, so now we are going to move on to problem 3, which is no calculator, no Desmos. So we're definitely going to have to make sure that we show our steps here a little bit more diligently, make sure we show our algebra, and really just justify any answers that we give. Number 3 says a student starts reading a book at time equals 0 minutes and continues reading for the next 10 minutes. The rate at which the student reads is modeled by the differentiable function r, where r of t is measured in words per minute. So this is a rate function. Just keep that in mind. Kind of like, think of it as like a velocity function if it were a particle motion problem. Selected values of r of t are given in the table shown. So we've got, we don't actually get the function, but we just get a few points on the function. Part A says approximate r prime 1, or the derivative of r at 1, using the average rate of change. Okay, so we did an average rate of change problem on the first, on problem 1. So hopefully you remember how to calculate that. You just basically use the slope formula over the interval 0 to 2. Show the work that leads to your answer, indicate units of measure. So r prime 1, okay, the slope of this function is approximately, and we're just going to use the slope formula using r of 2 and r of 0. So r of 2 minus r of 0 over 2 minus 0. Okay, that's your setup. And then we're going to go ahead and use the table to identify r of 2 and r of 0, which is going to be 190 respectively. So we've got 100 minus 90 over 2 minus 0. And honestly, like, you can actually just be done there. The units are words per minute squared. And these numbers are just so small and easy to work with. I almost can't even help myself but actually simplify. But if you're really taking the test, all year I've said don't simplify on these free response questions. So I'm kind of doing the opposite of what I would want you to do. You really want to stop here. Just in case you make an arithmetic error, but if you went ahead and simplified, you would have got 5 words per minute squared. Make sure you include those units, the words per minute squared, because r is words per minute. So if you're differentiating words per minute, it's going to be words per minute, or words per minute squared. Part B says, must there be a value C in between 0 and 10 such that R of C is 155? Now, this one is probably like the trickiest. It's not even that hard. Like, there's no algebra or anything here. I think, as I worked through all these, this one was like the trickiest one for me to really say in a succinct way. But basically, this comes down to the intermediate value theorem. Notice how at t equals 0, r of t is 90. And when t is 10, r of t is 162. And so the intermediate value theorem says that as long as this function is continuous, then r is going to hit every value in between 90 and 162. And so, yeah, 155 would be a value there. So as long as the intermediate value holds, we can go ahead and say, yes, there must be a value c that fits this condition. So the tricky part about this, I think, is understanding that the intermediate value theorem requires that the function is continuous, and that is not something that is explicitly stated in this problem. So you cannot assume it's continuous. In other words, it's not going to be good enough to say, yes, there is a c value where r of c is 155 because of the intermediate value theorem. The real question is, like, how do you know that the intermediate value theorem holds? And that has to do with the fact that although they don't tell you that this is a continuous function, they do give you the fact that it's a differentiable function. And something to know about the relationship between differentiability and continuity is that if a function is differentiable, it must be continuous. In other words, differentiability implies continuity. Okay, so if a function is differentiable, it must be continuous. And if a function is continuous, then the intermediate value theorem is going to hold. So how do we write this out in a succinct way? I think I'll do my best here, but this is what I'm going to say. I'm going to say R is differentiable. That was given. Differentiable. Therefore, R is continuous. Okay. Some other things we want to note here is that R of 0 is 90. Okay, R of 10 is 162. Okay, since R is continuous, the intermediate value theorem, or I should say, since R is continuous on the interval 0 to 10, the intermediate value theorem applies. Okay, since 155 is in between R of 0, which is 90, and R of 10, which is 162, there must be a value c I'll just, go ahead and spell it out. For 0 is less than c is less than 10, such that R of c is 155. There probably is a more efficient way of stating that out, but basically the key point I think that most students are going to miss is identifying how we know that this function is continuous. Okay, and it's because it's differentiable. So since R is differentiable, R is continuous. Since R is continuous, the intermediate value theorem holds from 0 to 10. Once you cite the values for R of 0 and R of 10, 155 is in between there, and so there must be a value c where R of c equals 155. That one's a little tricky. I'm not going to lie about that one. I'm really interested to see how they're going to point that out, because usually on the scoring guidelines, they're pretty, they kind of give you a pretty efficient way of getting all the points. So I'm really curious to see if what's the least amount you could write here and still come away with all the credit. Okay, C is a little bit more straightforward. It says use a trapezoidal sum with 3 subintervals indicated by the data in the table to approximate the value of the integral from 0 to 10 RT dt. Show the work that leads to your answer. So they tell you exactly what to do. Use a trapezoidal sum. So from 0 to 10 RT dt, we're going to approximate that. So let's look back at our table. Okay, so the first interval. And remember that with these Riemann approximations, there's Riemann sums, specifically the trapezoidal sum. What we're doing is we're creating, these are points on a graph, right? We got 0, 90, we got 2, 100, we got 8, 150, and 10. This is just a rough sketch. We're not really going to use the sketch for how we're going to solve this out. Really just want to clarify like what it is we're doing. So the formula will make a little bit more sense. And then 10's at 162. That's going to be like above here somewhere. So basically what we're going to do is we're going to construct trapezoids like this, find the area of each trapezoid and add them together. So the way you find area of a trapezoid is you average two bases, multiply by the height. In this case, the quote-unquote height is the length of the interval. That first length is 2, the next length is 6, and the third one is 2. So we're going to multiply that length of the interval by the average of the other two side lengths, the partitions, which like in the first case would be 90 and 100, and then add the area of each of those trapezoids together. Okay, so let me zoom out just a little bit so we can see this a little easier. So here we go. So for the first trapezoid, we've got a distance of 2. The interval is the length 2, and we're going to multiply by the average of 190. Okay, so that's going to find the area of that first trapezoid. The second trapezoid is going to be 6 times the average of 100 and 150. And then the last one is going to be 2 times the average of 150 and 162. Okay, now that's it. That's all you need here. You do not need to go any further than this. Okay, that is your answer. Do not waste your time trying to calculate what that actually equals. I know it's really hard sometimes to resist the urge to go ahead and simplify that out, but just don't. Just leave it at that. You don't have to go any further on a free response question. If you happen to calculate it out, it does equal 1,252, but there's no reason to go any further than that. Okay, the last part of question 3 is part D. It says a teacher also starts to read. I love this context here with the student and the teacher reading. At time t equals 0 and continues to read for the next 10 minutes. The rate at which the teacher reads is modeled by the function w defined by wt, and that is given, where w is measured in words per minute. So w is going to be a function similar to r in that it is measuring the rate at which a person is reading. R is measuring the student, and w is measuring the teacher. Based on the model, how many words has the teacher read by the end of 10 minutes? So we are going to treat this as like an accumulation problem. So we are going to accumulate all the words that we're reading in between time equals 0 and time equals 10. In other words, we're going to find the integral from 0 to 10 of wt. That's our setup. I think if you write that down, you're probably going to get a point. Although, again, once the scoring guidelines come out, we can verify that. So this is going to equal the integral from 0 to 10 of -3/10 t squared plus 8t plus 100 dt. We need to find the antiderivative of that polynomial, but it is just a polynomial function, so we could just use the anti-power rule to do that. We're going to increase that power by 3. So 3 divided by 3 is just 1, so this is just going to turn into -1/10 plus t squared, and 8 divided by 2 is 4. And then plus 100t, and we're going to go from 0 to 10. Okay, so the next step really should be our last step. Again, we do not want to be doing too much simplifying. We want to avoid as much simplifying as possible, but you do need to go ahead and show those numbers getting plugged in there. So we're going to plug in 10, we're going to plug in 0, and we're going to be done. So this is going to equal -1/10 times 10 cubed plus 4 times 10 squared plus 100 times 10, all that minus, and you might recognize that, hey, if you plug in 0, this whole thing is going to be 0, but you don't necessarily have to. You can just go ahead and plug that in. And yeah, this whole second expression is just going to be 0, but you're also okay just leaving it like that. That is your answer. It's that many words. Okay, if you happen to do the computation here, you're going to get 1,300. And actually, the computation doesn't work out to be that bad, but don't do it. Don't waste your time trying to figure out what that is. Okay, that's question 3. Let's move on to question 4. Number 4 says the continuous function f is defined on the closed interval -6 to 12. The graph of f consisting of two semicircles and one line segment is shown in the figure. Let g be the function defined by the integral from 6 to x of f of t dt. Part A says find g prime 8. Okay, so if g of x is the integral from 6 to x f of t dt, then g prime is going to be the derivative of that. And the fundamental theorem of calculus gives us how to compute this integral, or the derivative of that integral, and it's just going to be f of x dx. Or sorry, just f of x. So if we want g prime 8, that's going to be f of 8. And we can find f of 8 by just looking at the table, or sorry, the graph, and identifying the y value associated with the point on the graph. So f of 8 is 1. Okay. It says give a reason for your answer. I'm wondering if they want you to actually call out that we're using the fundamental theorem of calculus. I don't know if that's the case, if you really need to do that, but that is the justification for how we're getting that derivative. Part B says find all the values of x on the open interval, negative 6 to 12, at which the graph of g has a point of inflection. Give a reason for your answer. So points of inflection occur whenever the second derivative changes sign. So if we know the first derivative, and we got that from part A, we know the first derivative is just f of x. The second derivative of g is f prime. Okay, f prime correlates to the slope of f. So we're really going to be looking at the slope of that to find the points of inflection. So points of inflection occur anytime that g double prime changes sign. So what we need to do is find the critical values of f prime or the subcritical values of f. In other words, where is g double prime equal to 0? Okay, so we need to figure out where that happens. So we want g double prime to equal 0, and g double prime equals 0 anytime f prime equals 0. So we want to know, we're basically trying to answer the question, when does f prime of x equal 0? Or where is it undefined? So let's look up at the graph, and we can see that on that interval from negative 6 to 12, and it is an exclusive interval, so we don't have to consider the endpoints. We do have an undefined slope right here, so maybe I'll say 0 or, always kind of forget the undefined, or undefined. And so we have one at 0. We have one at 6. Slope is going to be undefined there. And we do have a couple places where the slope is 0. Slope's going to be 0 at 3. So we got 0, 3, 6, but also at negative 3. So we've got basically 3 points where we have a potential point of inflection here. And so let's see where that happens. So what I'm going to do is construct a number line chart for g double prime, okay, which is the same as f prime, which we just established there. And I'm going to put a couple numbers on here, all these potential points of inflection, negative 3, 3, and 6. And 0. Let's not forget 0. And is that all of them? Negative 3, 0, 3, and 6. Yeah, I think we got them all. Okay, so now what we need to do is find out whether or not g double prime or f prime is positive or negative in each of these intervals. So we're just going to be looking at the graph here. So if we look between negative 6 and negative 3, and I'll highlight that here on the graph, we can see that we have a negative slope here. So we know that in between those values, and actually maybe I'll just block it off here, between negative 6 and negative 3, we know the slope is negative. Now, between negative 3 and 0, we can see that the slope is positive. Okay, it's actually also positive between 0 and 3. So there we do not have a sign change. Okay, we do have a sign change at negative 3, but not at 0. Then we're going to look at the interval between 3 and 6, and we can see that that slope is negative. And then the slope between 6 and 12 is positive. So we have a total of what looks like a sign change at negative 3. We have a sign change at 3. And we have another sign change at 6. So we have a total of 3 points of inflection here. So it says final values of x, where g has a point of inflection. Our answer is going to be x equals -3, 3, and 6. And the reason for my answer is because at those x values, g double prime changes sign. Okay, we don't really need to cite whether it's going from negative to positive or vice versa, because in both cases we do have a point of inflection. So yeah, there we go. Now, if I'm looking at my work, I might have a little issue with this last statement here because I'm really just kind of asking myself what that is. I maybe don't write that last statement because you don't want to say anything equals undefined. It's a little taboo to write it that way. So I'm going to go ahead and erase that just so we're not confused about what we should be writing down. Okay, C says find g of 12 and g of 0. This one's pretty straightforward. We're just going to evaluate the actual function g here. Just as a reminder, g of x is the integral from 6 to x, ft dt. So g of 12 is the integral from 6 to 12, and we're just replacing 12 with every instance of x, which is just that upper limit of the integral. And g of 0, might as well set that up as well. It's going to be the integral from 6 to 0 of f of t dt. Now, one thing I'm noticing here is that we could probably solve this out, using calculus, but because of this piecewise function has just nothing but linear and circular parts, we can just use some basic geometry area formulas to come up with these. But if we're going to approach it that way, then we want to be careful with this g of 0 because 6 is actually greater than 0. So we might want to rewrite this as the opposite of the integral from 0 to 6. That way we can just look at the area outright and get our answer a little bit faster there. So the first one, we're finding the area between 6 and 12 to find g of 12. So that area is the area under the curve right here, and we can see that this shape is just a triangle, and the area of a triangle is half base times height. So while you could go through and figure out what that function is, and then integrate it, find the antiderivative, and so on and so forth, it's not really worth it. If you just recognize it's the shape of a triangle, we can just do half base times height, which in this case would be half times 6 times 3. Right, the distance here being 6, the distance here being 3. And so let's see, you could actually just be done there, right? Like box your answer. There you go. Now, if you actually calculate it out, if you couldn't help yourself, that's going to be 9. But with all these, don't bother simplifying. Once you get an arithmetic expression, you want to just be done. Okay, for the next one, we're going from 0 to 6, and we are going to have a negative area here because originally our integral is from 6 to 0, so it should be the opposite of 0 to 6. But if we just approach it as from being between 0 and 6, we can see that the area is this semicircle here, which is half of a circle. So we don't need to find the equation for that or anything like that. We're just going to use our formula for the area of a circle, which is pi r squared. We're going to cut it in half, and that's going to be that. So we're going to have half, don't forget the negative there. We're going to have half pi r squared, so half times pi times the radius, which we can see either going vertically or going to the side, is 3. So 3 squared, and we are done there. If you were to simplify this, there's really not a lot to simplify here. 3 squared is 9. You get negative 9 pi over 2. So don't write it like that. Just stick with this. You'll be less likely to make a mistake. Letter D, it says find the value of x at which g attains an absolute minimum on the closed interval. So here we have another extreme value theorem problem, just like we did on the first problem. So a little repetition here between the non-calculator and the calculator one. We're going to approach this just like we did on problem 1. We're going to find the critical values, we're going to find the endpoints, we're going to calculate the value of the function g at each one, and then in this case, since we're looking for a minimum instead of a maximum, we'll be looking for the smallest value in that table. So just a couple little notes here. We know g prime, we've already established this, is f of x. I'm just going to write it down one more time here because we're kind of scrolling down too far to see the other one. And so we want to find where is, so my critical points are going to be where g prime of x equals 0. Okay, in other words, where f of x equals 0. So let's figure out where f of x equals 0. Okay, so if we go back up here, we're looking for, this is the value of f. So we've got a few numbers here. We've got one at -6, 0, 6, and that's it. My endpoints, so -6, 0, and 6. My endpoints are obviously going to be -6 and 12. We've already accounted for -6. We don't need to write that twice. But now we're ready to set up our table. And the table itself is the justification here. So we've got x with -6, 0, 6, and 12. And then we have g of x, which is, you don't need to write this down, but it's the integral from 6 to x f of t dt. In other words, it's the area under the curve. Now, if we plug in -6, for instance, we are going to be evaluating the integral from 6 to -6, okay, of f of t dt. Now, 6 is bigger than -6, so if we're going to approach this from like an area perspective, it might be helpful to write this as negative integral of -6 to 6 f of t dt. But we're going to see once we scroll back up to the graph that it really doesn't matter if you do that in this case, because from -6 to 6, we have the same amount of area below. Let me erase some of this so it doesn't get, let's just erase everything here. We have the same amount of area below the x-axis as we do above the x-axis. Now, we've already found the area of each of these individual semicircles in part C. We found that they were negative, or they're 9 pi over 2. We've got one positive and one negative. They're both going to cancel each other out and just give us 0. So whether or not you have positive 0 or negative 0 doesn't really make a difference. So yeah, this is just going to be 0. Okay, now if we look at when x is 0, we have the integral from 6 to 0 f of t dt, and we actually already evaluated that, right? We evaluated that up here. So we don't need to do it again. We could just say that it's negative 9 pi over 2. Now, if we plug in 6 and we have the integral from 6 to 6, the integral of, anytime your upper and lower limits are the same, your integral is just always 0. And then finally, we've got the integral from 6 to 12, f of t dt. This is one that we already solved over here. We saw that that was 9. Okay, so if we're looking for the absolute minimum, we're looking for the smallest value on this list, and that's going to be negative 9 pi over 2. Okay, so we want to say something kind of similar to what we said on problem number 1. I'm going to say the absolute minimum whoa. What happened there? All right, that looks a little better. The absolute minimum of g of x on the interval -6 to 12 occurs at x equals 0. Yeah, that's it. It doesn't actually ask for what the minimum is. It's just asking where it is, what is the x value where that happens, and that's it. We don't really need to say anything else. The justification is just the table. So that table of values that we just constructed, that's all we need for the justification. Okay, that's it for number 4. Let's take a look at number 5. Number 5 says 2 particles h and j are moving along the x-axis. Between times 0 and 5, the position of particle h at time t is given by that xh equation, the function, and the velocity of particle j is given by the vj function given there. Part A says find the velocity of particle h at time equals 1. Show the work that leads to your answer. So let's first figure out what is v of h. So or not v of h, but vh of t. So it says find the velocity of particle h. Now, the velocity of particle h is the derivative of the position. So I know in years past, you have to make that connection to get all the credit. So make sure anytime you're answering any of these particle motion questions, that if they give you either position, velocity, or acceleration, and they're asking about like one of the other ones, that you always make that connection with velocity being the derivative of position, or let's say it was asking for acceleration. Acceleration is the derivative of velocity or the second derivative of position. So you have to make that connection if it's not explicitly stated. Okay, and so this will be the derivative of xh of t, which we're just going to use chain rule here. So it's going to be e to the t squared minus 4t times the derivative of the t squared minus 4t, which is 2t minus 4. So that's going to be our function for the velocity of particle h. And now we're going to evaluate that at t equals 1. So the velocity of particle h at t equals 1 is going to be e to the 1 squared minus 4 times 1 times 2 times 1 minus 4. Now that's it. We're not going to go any further. That is the velocity. There's no units here, so we don't need to say anything. We're just going to go ahead and box our answer. Make sure that you're not writing too sloppily here. Might be better to differentiate this times and minus by putting the 1 in parentheses here. Now, if you did go ahead and simplify it, which I am not suggesting that you do, you would get negative 2 times e to the negative third power. But I would just leave it like that. Remember, you do not have to simplify any arithmetic on these free response items. Part B says, during what open intervals of time are the particles of H and J moving in opposite directions? Give a reason for your answer. Here's another one that I think is a little challenging. At least in my class, it had historically been challenging for students to remember that in order for objects to be moving in opposite directions, the velocity of both of these have to have different signs. Okay, so the sign of the velocity is what's telling you which direction that it's moving in. So what we need to do is we need to analyze the sign of VH and the sign of XH, the VH and VJ, the two velocities of the two particles, and figure out like when are they positive, when are they negative, and to answer this question, we need to say like, when are they different? Okay, so we've got basically two things here. One is VH of t. When is that 0? What we want to do is construct like a number line here for both the velocity of particle h and the velocity of particle j, and keep track of when are they positive and when are they negative. Now, the only times that their signs can change would be whenever the function is either undefined or 0. Now, the function h, vh, is never going to be undefined for any values of t, so we don't have to worry about that. We're just looking for where it's 0, and then we also need to do the same thing for the velocity of particle j. We're looking for where that's 0. Again, the reason why we're looking for where these things are 0 is to make partitions on our number line to where we can see when the sign is changing. So let's start with the velocity of h. Okay, we already came up with that equation up here, and so we want to know when is this thing equal to 0. So in other words, when is e to the t squared minus 4t times 2t minus 4 equal to 0? Let's write that a little clearer. And this is already this is a factored expression, and so we can use the zero product property to say, oh, this is only going to happen, or this function is going to equal 0 anytime each of the factors are equal to 0. So either that e expression is equal to 0 or 2t minus 4 is equal to 0. Now this one right here can never equal 0 because it is an exponential function there. So this is never going to be 0. But this one could be 0, and it's going to be 0 when t is 2. Okay, so I'm definitely going to want to include 2 on my number line. I'm gonna hold off on labeling anything quite yet. Okay, so the velocity of j is equal to 0. Let's look at that equation. That's going to be 2t times t squared minus 1. We can use the zero product property here as well. 2t could equal 0 when t is 0, and t squared minus 1 is going to equal 0 whenever t is either plus or minus 1. So we've got all these values where we have a potential sign change on the velocities of v and or j So let's label all these numbers on our number line. So it looks like the smallest number is going to be -1, and then we've got 0, 1, and then 2 over here. Now, the only, you know what, I'm going to label 2 above, because that corresponds with the critical value, or not the critical value, but the value when the velocity of particle h is 0. So now what I need to do is figure out, okay, let's start with the velocity of particle h. When is that positive and when is it negative? There's only really 2 intervals there, everything before 2 and then everything after 2. So we could pick any number we want and plug that into the function for VH. Sorry about the bell there. We're going to plug that into VH. So let's see here. So let's pick like 0, for instance. If we plug in 0 for VH, and VH is right here, we're going to get e to the 0th power, which is 1, times 2 times 0 minus 4 is going to be negative. So V of h is going to be negative on this entire interval. Now, if we plug in a number like, let's say, 10, then we're going to get a positive number times another positive number, and it's going to be positive there. Okay, so now we're going to do the same thing, but with j, and we just have a few more intervals to consider here. We've got 1, 2, 3, and 4 intervals to consider for the velocity of j. Again with the bells, yeah. Sorry, so we have 4 intervals that we need to consider for the velocity of j. So let's say you want to pick a number like a representative from that leftmost interval, like -10. We're going to get a negative times a positive, which is going to be negative. So negative here. In between -1 and 0, if we plug in a number like, say, -0.5, we're going to get a negative times a negative, which is positive. If we plug in a number like +1/2, then we're going to get a positive. And I'm looking at, by the way, I'm looking at this equation right here. So I'm really just thinking about 2t times t squared minus 1. And so that's where, when I'm saying like a negative times a positive or whatever, I'm thinking about those 2 expressions. So like if I plug in 1/2, for instance, I'm going to get a positive number times a negative number, which is negative. And if finally I plug in a number like 2, I'm going to get a positive number times a positive number, which is positive. So now I've figured out where the velocity of particle h is positive, negative, and I've done the same thing for the velocity of particle j. And so in order for them to be moving in opposite directions, they need to have opposite signs. And so I'm just going to like look up and down my number line and see where those opposite signs occur. Like for instance, they're opposite in between -1 and 0. Between -1 and 0, the velocity of h is negative and the velocity of j is positive. And then they're also opposite between 1 and 2. Okay, we've got an interval right here where the velocity of h is negative and the velocity of j is positive. So we have 2 intervals here. We've got, let's see, we're running out of space to write all this out, but I guess my answer here is going to be between -1 and 0 and between 1 and 2, okay? And I'm going to say because, and we could be just kind of brief about here, VH and VJ have different signs. I think that should be all you need to get those points. This one is definitely kind of involved. It's definitely one of the ones that, hey, if you lose some points here, no big deal. You can still get a 5. It's not really that hard, but there's like a lot of detail in this particular problem. Okay, part C. It says it can be shown that the derivative of the velocity of j, again, that's acceleration, just make a mental note of that, is positive. Is the speed of particle j increasing, decreasing, or neither at time equals 0? Okay, so be careful here. When you're talking speed, speed's different than velocity. Speed is the absolute value of velocity, and you know that speed is going to be increasing if both the velocity and the acceleration have the same sign. If they're sort of working together, it's going to increase the speed. The speed will be decreasing when velocity and acceleration are working against each other. In other words, when they have opposite signs. So let me just write that out. So the speed is increasing when velocity and acceleration, which we'll just call f prime, have the same sign. and the speed is decreasing whenever v and the velocity and the acceleration have different signs. Don't write any of this information out, but this should be what you're thinking. Okay, so at time equals 2, first of all, we know v prime is positive. So we know the acceleration of j is positive. So now we just need to find the velocity of j at 2. Okay, so velocity of j, which is given up here, 2t, so 2 times 2 times 2 squared minus 1 cubed. Now, if you can just tell the sign here, you can be pretty much done, but this is like one case where I think doing the arithmetic is worth it. You don't necessarily have to do all the arithmetic, but we need to know whether or not this is positive or negative. 2 times 2 is 4. That's going to be positive. 2 squared is 4. 4 minus 1 is positive. So yeah, this is positive. Okay, so we're basically done here. Particle J, particle J's speed is increasing at time equals 2, and we need a reason here because the signs of v and v prime, which is the acceleration, are both, or you know what, let's just not even go there. Let's say that they're the same. Okay, because they could both be positive or they could both be negative. In this case, they're both positive, but it doesn't really matter. In either case, it'd be increasing. And so we're just going to say because the signs are the same. So yeah, answer here is increasing. Okay, part D says particle J is at position x equals 7 at time equals 0. Find the position at particle J at time equals 2. So this is going to come down to a fundamental theorem of calculus problem. We're going to set up an equation to use with an integral and an initial condition to find the position at time equals 2. So one thing we need to note here is that the velocity is the derivative of the position. Okay, that connection needs to be made just like we made it in part A. And we already made it in part A, so I don't know. Oh, you know what? We were talking about H, not J, so I think it'd be worth writing it down just right off the top. So because that relationship exists, we can come up with an integral between 0 and 2, which are going to be the two times we're interested in, time equals 2 and time equals 0, of Vj dt. And that's going to equal, using the fundamental theorem of calculus, xj at 2 minus xj at 0. And that's because v is the derivative of x. Okay, so we can only make this statement using the fundamental theorem because we know this to be true. And so if we're solving for the position at time 2, we just need to isolate the xj2 here. We're just going to isolate this and add the xj0 to both sides. So xj2 will equal xj0 plus the integral from 0 to 2 of vj t dt. Okay, so xj0, that's given. It's 7. Okay, we know that one right off the bat, but we need to evaluate this integral. And to do that, we need to find the antiderivative of Vj. Now, let's go back up to see what Vj actually was. Vj was 2t times t squared minus 1 to the power of 3. Oh, okay, so we're going to have to do a little u substitution there. Actually, let me write that out. 2t times t. Okay, so we're going to do a little side workout over here. The indefinite integral of 2t times t squared minus 1 cubed dt. If we need to find the antiderivative of that, what we need to do is do a little u substitution, it looks like. So we're going to let u be t squared minus 1. So I'm going to say let u be t squared minus 1. And therefore, du is going to be 2t dt, which we actually have a perfect match for here. Very nice there. So the integral of u cubed du would be 1/4 u to the fourth plus c. So that 1/4 u to the fourth, that's going to be our antiderivatives of Vj. So now let's go back to our, maybe I'll just separate this out a little bit. Okay, we're going to use this. So actually, let's go back and plug in that u just so that we have an expression we can work with here, which is 1/4 times 2t. Maybe we could just simplify that. 1/4 times 2 is 1/2, but I'm going to just leave it like that for now. 1/4 times, oh no, we're going to have to raise it to the fourth power, so that won't work anyway. 2t times t squared minus 1 cubed to the fourth. Ugh. It's kind of gross, but that's what it is. Oh, no, no 2t. What am I doing? Oh, that's sloppy. Let's fix that. It's just u to the fourth, so it's just t squared minus 1 to the fourth. Yeah, okay. Now we're looking a little better here. So now let's go back to our problem. We've got xj2, which is what we're trying to find, is xj0, which we already said was 7. That was given, plus we integrated, or we found the antiderivatives of vjt. It's 1/4 times t squared minus 1 to the fourth power from 0 to 2. So we're going to plug in 0, we're going to plug in 2, and then we're going to be done. We're not going to do any of the arithmetic. So this is 7 plus, let's start by plugging in 2. Okay, 1/4 times 2 squared minus 1 to the fourth. And now we're going to plug in 0. 1/4 times 0 squared minus 1 to the fourth. And that's going to be our answer. Do we have units here? No, we haven't had units the whole time, have we? So that's it. Now, if you happen to simplify that, and the simplification, it's not too bad. There are some fractions that, it looks like with the 1/4, we're going to have some fractions to worry about. You do get a nice clean 27 if you do work that out. But just like all the other ones, don't worry about doing the arithmetic. Just be done once you plug everything in. Okay, well, that is number 5. That brings us to the last problem, number 6. Number 6 says, consider the curve G defined by the equation y cubed minus y squared minus y plus 1/4 x squared equals 0. Part A wants us to show that dy dx is negative x over 2 times 3y squared minus 2y minus 1. So what's kind of nice here is they actually do give us what dy dx is. So you just need to show how you get there. Luckily, you don't have to, you don't have to be wondering whether or not you did it right or not, because if you do the algebra and it turns out to look like that, you know you did it right. So what we need to do is we need to differentiate both sides of this equation with respect to x. Notice that it's asking for dy dx. So we do want to differentiate with respect to x. In other words, we want to take the derivative of both sides of this equation with respect to x. And we can do that by just differentiating each term individually here. Now, if the term has a y, then we are going to have to use the chain rule, and the derivative of y with respect to x is dy dx. So that first term is going to be 3y squared times the derivative of y with respect to x, so dy dx. The next term will be, minus 2y dy dx. The derivative of negative y is just minus dy dx, or you could write it as like minus 1, which might be helpful later when we do the factoring. And then we want to differentiate that last term is in terms of x, so dx is just 1. We're not going to have a separate like dy dx term on this last one. It's just going to be, 2 times a fourth is a half, so we have plus 1/2 x. And the derivative of 0 is just 0. So we have this, and basically what we want to do is we want to separate all the terms that have a dy dx and put those like on the left-hand side, and then we're going to move that 1/2 x over the right-hand side. I think we can kind of get away with doing both of those steps at once. First, I'll just factor out that dy dx is a GCF. So dy dx times 3y squared minus 2y minus 1 equals, and if you subtract 1/2 x from both sides, you get negative 1/2 x. Or negative x over 2. Maybe it makes more sense to write it like that. So I'm actually going to write that as minus x over 2, just so that it looks a little bit more like what we're seeing the formatting on the problem. Like in other words, like you have this minus x over 2. This right here is the same thing as negative 1/2 x, but I'm just going to rewrite it like that so it looks like what we're going for here. Lastly, we want to divide both sides by that quadratic expression in the parentheses to isolate the dy dx. It's going to be our last step here, and that's going to give us our answer. So we have dy dx equals negative x over 2 times 3y squared minus dy minus 2y minus 1. And that's about it, okay? There's not really, it's just trying to show how you get there. I don't think there's going to be, I did kind of take some liberties not showing every little step, but I think we're showing enough here to get full credit. Once the scoring guidelines come out, I'll definitely review this and make sure that I'm not missing any intermediate steps that they're looking for. Part B says there is a point P on the curve G near 2, negative 1 with an x-coordinate of 1.6. Use the line tangent to the curve at 2, negative 1 to approximate the y-coordinate of point P. Okay, so here we're going to approach this like we would any other linear approximation problem. We're going to need a point, we're going to need a slope, and we're going to write our equation in y minus y1 equals m times x minus x1 form. That's point-slope form. So the point that we're going to be using is 2, negative 1, and what we need is the slope at that point. So let's calculate out that slope here. I'm going to erase this just to give myself a little bit of room to work here. We do have the slope formula, so even if your algebra messed up and you didn't get any points on A, they do give you the slope formula here, so you can still get part B even if you don't get part A. So the slope at 2, negative 1 is going to be negative 2 over 2 times 3 times negative 1 squared minus 2 times negative 1 minus 1. Okay, so this is the slope particularly at 2, negative 1. One way to write this, I suppose, is you could write it as like the dy dx at 2, negative 1. Okay. Now, let's go ahead and simplify that. Let's see, we get negative 2 over, let's see, negative 1 squared is 1. So we get 3 plus 2. 3 plus 2 is 5, minus 1 is 4. 4 times 2 is 8. So it's going to be negative 2 over 8, which is the same thing as negative 1/4. So that's going to be the slope we use in that point-slope form equation that we're going to use for our tangent line approximation. So let's write it out. Y minus y1. 1 minus negative 1 would be y plus 1 equals negative 1/4 times x minus 2. Okay, so that is our tangent line at 2, negative 1, and we're going to use that to approximate the y-coordinate of point P. So we're going to say y at P, at point P, is approximately negative 1/4 times the x-coordinate, which is 1.6, minus 2, minus 1. Okay, that minus 1, by the way, is just coming from subtracting this plus 1 on both sides. So now we're going that's it. That is the y-coordinate. You can simplify it, but because we have an arithmetic expression that's logically equivalent to whatever we would end up getting, I would just say stop there. Okay, if you simplify that all the way, you do get negative 0.9, but it's totally not necessary to do that. Okay, just leave that arithmetic expression alone. Hopefully that is a big takeaway from watching me work all these problems, is that on these free response questions, don't open up yourself to making arithmetic errors. You should be doing very minimal arithmetic on these non-calculator problems. The calculator problems, yeah, you probably need to do some arithmetic, but it's all going to be done in the calculator anyway, so you don't actually have to do it. With these very minimal, you do have to calculate that slope out. I suppose you could get away here. If you did not want to do the arithmetic on that slope, you could say yp equals, or approximately equals, although they don't take off points for equals versus approximately, so you don't have to worry about that. But you could say, instead of writing negative 1/4, you could just say negative 2 over 2 times 3 times negative 1 squared minus 2 times negative 1 minus 1, and let that be times 1.6 minus 2 minus 1, and that will work too. Yeah, that would be kind of the safest way, but that looks pretty ugly. And, now we're running the risk of maybe we didn't close a parenthesis here or there. That could work, but I'd be a little hesitant to do that, just only because of the parenthesis issue there. If you're missing one parenthesis, you don't write this just the right way, you might lose a point there. So I'm not even going to write it that way. I think simplifying that fraction is pretty easy anyway, and maybe you do a little bit of arithmetic, but for the most part, you shouldn't be doing too much. Part C says for positive values of x and y, there's a point S on the curve at which the line tangent the curve is vertical. Okay, so for it to be vertical, that means the slope is undefined. Okay, the only way for a slope to be undefined here is if we're dividing by 0. We run into a divide by 0 error. So that means that this denominator is going to have to be 0. So it says find the y-coordinate of the point S. Okay, so in other words, we have a vertical tangent. Okay, that implies that we have a undefined slope. Okay, which means that the denominator must equal 0. Okay, so I wouldn't write any of that, when you're actually working this out. But I just want to give you a little background on what your thought process should be as you get set up with this problem. So let's take that denominator, which is 2 times 3y squared minus 2y minus 1 equals 0. Set it equal to 0, and then solve for y. So here we could divide both sides by 2 and get 3y squared minus 2y minus 1 equals 0. Here's kind of an unusual factoring where the leading coefficient's not 1. Luckily, all the numbers are pretty small, so factoring shouldn't be too terrible here. But usually that leading coefficient's 1, so I'm a little surprised that they threw in one at you that had a leading coefficient of 3, but it is what it is. And so just kind of moving forward, I'm going to know that I can stop saying, hey, they're mostly going to be 1, because this one clearly is not. So it does factor pretty nicely, though. We get 3y plus 1 times y minus 1. And using the zero product property, we can set each one of those equal to 0 and solve them individually. And we get y equals negative 1/3 and y equals 1. Now, we're really only looking for positive values of y. So we're going to eliminate that negative 1/3 because y's got to be positive. So therefore, our answer is y equals 1. And that brings us to our last problem here. It says a particle moves along curve h, defined by the equation 2xy plus natural log y equals 8. At the instant when the particle is at the point 4, 1, the derivative of x with respect to t is 3. Find dy dt at that instant. Show the work that leads to your answer. So let's start with the equation that we're given here. 2xy plus natural log of y equals 8. And we want to differentiate this with respect to t because we're trying to find dy dt. So the only way we're going to get a dy dt out of this is if we differentiate with respect to time. So so let's go ahead and do that. Now, we want to be careful because that first term is a product. So we are going to have to use product rule here on the first one. Just to recall, when we're trying to differentiate a product, let's say f times g, and we're going to have f prime g plus fg prime, okay? You may have learned it a little differently if you're not in my class, but that's how I presented it in class. So the first function being 2x, second function being y. So let's be very careful when we're differentiating this. We should get the derivative of 2x with respect to t is just going to be 2 dx dt times y. So that's like my f prime g, okay, plus fg prime, f being 2x and g prime being the derivative of y with respect to t. Okay, and I guess maybe one thing I should probably write out here and make this very clear is I am differentiating with respect to t. So I'm saying d dt on both sides. Oh, didn't leave myself enough room there. D dt of 0. Of 8. It will be 0, but of 8. 2x dy dt, and that is the end of the derivative of that first term. The derivative of natural log of y with respect to t is going to be 1 over y dy dt. Okay, derivative of natural log of y is 1 over y. Using the chain rule, we get dy dt. And the derivative of 8 with respect to anything is just going to be 0 because 8 is a constant. Okay. So we're trying to find dy dt at this instant. So we need to isolate dy dt. And so we see that there are a total of two terms that have the dy dt. We've got this 2x and we've got the 1 over y. And so we're going to factor out the dy dt out of that expression. And then we're going to move everything else to the right-hand side. So kind of like we did up here with the first problem, okay? So I'm going to factor out that dy dt. So dy dt times 2x plus 1 over y is equal to 2 times negative 2, sorry, dx dt times y. And then I'm going to divide both sides by the 2x plus 1 over y. So I have negative 2 dx dt times y over 2x plus 1 over y. All right, so that's my expression for dy dx. Now, at that particular instant, we're going to have to do a little evaluating here. We're going to plug in all the information that we know. So we know dx dt is 3, so we're going to plug that in. We also know x is 4 and y is 1. So all we need to do is just substitute all those numbers into our formula there, and then we'll have our answer. So we have negative 2 times dx dt, which at that instant is 3, times y, which is 1, all over 2 times 4 plus 1 over 1. That is going to be our answer. You can leave it like that. If you do simplify it, which is totally fine, let's see what we get. It'd be negative 2 times 3 is 6, 2 times 4 is 8, plus 1 is 9, so you get negative 6 over 9, which would be negative 2/3. Do not bother simplifying that, but if you did, that's what you should get. And that is going to wrap this up. We've now done all the free response questions on the 2025 AP Calculus AB exam. Hopefully you feel pretty good about your answers here if you took this last week. If you have any questions, please reach out. As always, thanks for watching, and y'all have a great day.